Okay, since we couldn't meet for class, here is all the ANOVA information that you need in order to do well on the final and kind of be equipped to understand research in life. If we look at the final, and this is the final, it's on D2L, the first part is going to be about ANOVA interpretation, some basic questions about ANOVAs. Then I'm going to give you output that looks like this, and you're going to have to answer these kinds of questions about it. What's the independent variable? How many groups? Variance percentages, and so on. So we're going to talk about that. There's also going to be a section on two-way ANOVAs. So again, I'm going to give you some output, some graphs, and you're going to have to interpret it for me. Continue. Some questions on correlation and regression, which will be next week. And then multiple regression at the end. And this is all on D2L. The multiple regression and regression output looks like this. And so we will be going over next week what this stuff all means. But for now, we're going to just confine ourselves to Introduction to ANOVA. Now, we have really 7 main topics. 1, what is ANOVA and how do we calculate it? You're not going to have to do math necessarily on the exam, some minor math, but really it's more about conceptually what's going on. Then we're going to talk about a one-way ANOVA in SPSS, but again, we're just going to look at the output. You guys won't have to work with it at all. We'll talk about the assumptions to the test. We'll talk about follow-up tests, family-wise error, two-way ANOVAs, and main effects and interactions, which is really something that gets interesting in two-way ANOVAs. So this is the rundown of the things you need to know about. So when we think of a one-way ANOVA, ANOVA stands for analysis of variance, and it's called that because it's really looking at the ratio between two different variances. One is the variance due to what group you're in, whether you have blue eyes, brown eyes, green eyes, whether you're a man or a woman, whether or not you are Democratic or Republican or independent. And then I'm going to compare that variance to the variance that is not explained by being in those particular groups. And so when we think about this idea more broadly, we think about how we describe a group of people, and we typically describe them by the average. The average American, makes $40,000 a year, has 1.2 cars, and a family of 5 with 2.3 children, right? Now, people are different from that. The question is, why are they different? And some of those reasons are due to some variables about their occupation, about whether or not they're married, about where they grew up, and so on. And some of that is just due to other stuff that's just kind of random, that we don't really know anything about. So if we look at how tall everyone is in the class, right, the vast majority of why people are a different height is due to their genetics, so what genetic group they belong to. A lot of that variance, though, is not explained. If we look at the heart health of people who smoke versus the people who don't smoke, right, the variance that's due to smoking or not is going to account for some piece of blood pressure. A lot of other stuff is not explained by smoking, and it's explained by other things like diet, stress, exercise habits, and so forth. Now, the nice thing about ANOVA, because so far it's kind of just like a t-test, is that I can compare more than 2 groups at once. When you were looking at the exam, right, you could compare 2 groups with an independent t-test, or you could look at how people changed over 2 different time periods with a paired samples t-test. ANOVA allows us to look at how people change over 3 time points or 4 time points, or we can look at how people are different, whether they're from 1 group, 2 group, 3 group, or 4 groups. Okay, so I use ANOVA when I kind of have a scope beyond just a basic t-test. So a simple example might be having some data. We have 3 different groups, and suppose that I have this on a 10-point scale, right? And I'm measuring people's aggression. If we look at this, we might ask some basic questions about how to read this graph, and you should all be pretty comfortable with this by now. How many people are total? Well, I have 3 people who have a score of 2. I have 3 people who have a score of 4, and 3 people who have a score of 6. So I have 3 plus 3 plus 3 gives me 9 people. I have 3 people at each level. My average or mean aggression rating is 4. If I added up 2 plus 2 plus 2 plus 4 plus 4 plus 4 plus 6 plus 6 plus 6, it would all balance out to an average of 4. And the last question I would ask myself is, why are people different? This is supposed to be aggression. Why do people have different levels of aggression? And suppose that I come up with this idea that it all has to do with eye color. That whatever color you're born with in your eyes, that's how aggressive you're going to be. And it's totally determined by it. In this case, we assume, as usual, that the null is true, though, that eye color has nothing to do with aggression. And for ANOVA, we write it like this, that the mean aggression of people with blue eyes is the same as the mean aggression of the people with green eyes, which is the same as the mean aggression of the people with brown eyes. In other words, all the means are equal. The alternative hypothesis is that at least one of those groups is different from somebody else. Okay? And we don't necessarily write out the alternative hypothesis in this case because it just takes on too many forms. Because it could be that blue is different from green, but not from brown. That blue is different from green and brown. That blue is different from brown and not green. Or that green is different from brown or brown and blue. And that just is a lot of busy work. We just alternatively say that at least one group is different. So suppose that I have this as my data, right? And I'm looking at whether eye color is related to aggression. I have all my blue people here. They have aggression ratings of 2. All my brown-eyed people have aggression ratings of 4. And all my green-eyed people have aggression ratings of 6. So if I think of the effect of eye color, and let's see if I can actually move this thing around here. I guess I can't. Why can't I? Let's see if this works. Doesn't work. So anyway, I can't use the animation. I'm trying to keep this video file small enough to upload, so I have a small portion of the screen highlighted. Ultimately, when we think about the effect of eye color, I'm talking about how it makes somebody different from the average. And as we've seen, right, there's an average value of 4 for aggression ratings, as we saw here. Now, the effect of having blue eyes is basically means that you have 2 points fewer on the aggression scale than the average person. The brown effect, or the effect of having brown eyes, is that you are exactly as average. There is no brown eye effect. The effect of green eyes is that you are 2 points more aggressive than the average. And notice in all those cases, I'm referring back to the overall average. And that's what the ANOVA is testing, whether or not you are same or different than the overall average. So when we look at the effect of grouping variables, we look at 3 things. 1, what basically are the differences that exist for everyone relative to the mean? So when I talk about the total squared differences from the mean, basically I'm saying people are different from the mean in general, right? And there is this total amount that if I compare person 1 to the mean, person 2 to the mean, person 3 to, and I add all that up, I get this total. Now that total splits into 2 different parts. One is the difference in the groups, or the means of the groups, meaning that the blue-eyed people are going to be different from the brown-eyed people, and the brown-eyed people might be different from the green-eyed people, and the green-eyed people might be different from the blue-eyed people. And so the question is, how much of this overall difference can be attributed to which group you're in? There is also another part of that can't be attributed to the group you're in because there are differences that exist within the groups. Now in our case so far we don't have that, but we're going to look at another example that does. So for example, suppose that I have my simple example of 3 blue-eyed people who all have a mean aggression rating of 2, brown-eyed people with a mean aggression rating of 4, and green-eyed people with a mean aggression rating of 6. I am just calculating my sum of squares just like I did when we were doing basic descriptive statistics and we were trying to calculate variance. When we were doing t-tests, right? We talked about sum of squares. And this is really all that I'm doing. And the sum of squares represents the kind of the total way that people are different from the mean. So if somebody's 2 points different from the mean, that's a squared value of 4. If somebody is not different from the mean at all, and again the mean here is 4, right? That's a difference of 0. And if somebody's 2 points above the mean, well again squared, that's another difference of 4. So in total, if I want to quantify how much people are different from the mean, I have the sum of square value of 24. Now one thing that we're going to be doing is organizing all this stuff. I have my total sum of squares in one chart. I'm going to look at the sum of squares that exists between the groups, and I'm going to look at the sum of squares that exists within the groups. And the between sum of squares and the within sum of squares add up to the total sum of squares. So just a brief way to look at this, right? If I'm thinking about how people are different based on the group they're in, what I'm going to do is look at this equation. I'm going to highlight, if I can here, this part right here. This is just saying that group 1, or the mean of group 1, is different from the overall mean, and the m with a little g means it's the grand mean. Okay, so this is the mean of each group. K stands for each group that I have, and the m sub g stands for the overall mean. So when I add everyone together and ignore that they're in groups, I get an overall mean. However, each one of my groups also has its own mean. So I'm comparing those two things. However, I want to square that difference to get rid of that whole negative problem, and I also want to multiply it by how many people are in each group. And so when we do all this, we come up with something that looks like this. I have 3 people in group 1. They have a mean of 2, right? They're 2 points lower than the overall mean of 4. I'm going to square that, multiply it by 3, right? So 2 minus 4 is negative 2 squared is 4, times 3, because I have 3 people, is 12. This is 0, squared is 0, times 3 is 0. This over here, 6 minus 4 is 2, squared is 4, multiplied by 3 is 12. So 12 plus 0 plus 12 gives me 24. And so I'm going to put the between sum of squares in my chart here. And I notice that it's the same as my total. In other words, because there is no difference within the groups, all of my reasons why people are different, all of my variability is due to group membership. So when I look at within group calculations, basically what I'm doing is a smaller version of sum of squares for blue, a small version of sum of squares for brown, and a small version of sum of squares for green. I do this by subtracting each blue score from the mean blue score. And in this case, because my mean blue score is 2, right? 2 minus 2 equals 0, 2 minus 2 equals 0, 2 minus 2 equals 0. Square all those, still get 0. Add them all up, still get 0. I do the same thing for brown. I do the same thing for green. I fill that in. Now comes the rest of our chart. And basically I need to fill in my degrees of freedom. And if I look at this, I have degrees of freedom, total, within, and between. The total is the total number of people I have minus 1. So in this case, right, I have 3, 6, 9 people minus 1. That's going to be a degree of freedom of 8. Between group degrees of freedom is the number of groups I have minus 1, or k minus 1. Again, k meaning the number of groups that I have. So in my case, right, I have 3 groups. So my between sum of squares is going to be 2. And I'll just put these in here. Now my within is always going to be total minus between. So 8 minus 2 will give me 6. Because these, the between and the within, have to add up to the total. So in this case then, right, I can figure this out otherwise by looking at each particular group. Oops. And looking at how many people I have in each group minus 1. And so it's going to be 3 minus 1 plus 3 minus 1 plus 3 minus 1 gives me 2 plus 2 plus 2 equals 6. I can also calculate it as taking the total number of people minus the number of groups. It's a shorter way to do it, and it works out, right? And in that way, again, I get 6 because I have 9 people, 3 groups. 9 minus 3 equals 6. Now the way that I figure this stuff out then, and now that I have this filled, is I'm trying to calculate my variances. And again, we call it mean squared error. It's the same thing as variance. So I have a between groups variance and I have a within groups variance. Excuse me. My variance, again, is always going to be my sum of squares divided by my degrees of freedom, just like it was when we were doing z-tests and calculating variance just by itself. So 24 divided by 2 equals 12. 0 divided by 6 equals 0. And 12 divided by 0 really equals infinity, but it's just, you know, a really, really, really big number. One of the things that I'll want you to be able to do is fill in this chart and know the relationships between each different cell, and we'll go through a few examples. The formulas for each one of these is in this, but it's more important for you to know, if I give you only part of this information, how do you fill in the rest? So let's do another example and then we'll try to fill in that chart. So suppose I have this. Now if you look at, right, each person, I have some variation within my groups. I also have 3 more people. So instead of 9 people, I have 12 people. If I want to do my calculations, right, I can do my overall mean, and I can start by filling in my between group sum of squares. I have, again, 4 people. I'm going to compare the mean of this group to the overall mean, and the overall mean in this case is 3. Square it, multiply it by 4. Do that same thing for the brown eyes, green, and basically, again, all I'm doing is saying how is each group different from the overall mean, and then I'm going to weight it according to how many people are in each group. And if I do that, I get this between sum of squares value of 8. If I do the sum of squares within, right, and I look at this, for the blue group, right, I have a mean of 2. This person is 1 away from 2. This person is 1 away from 2, 1 away from 2, 1 away from 2. If I square that, I get my 1s. 1 squared is 1, 1 squared is 1, 1 squared is 1, 1 squared is 1. Sum of squares add up to 4. If I look at my brown group, I'm looking at how people are different from the mean of that group. Well, this person is 1 below the mean. The average group of, or the average rating for the brown group is 3. And again, 1 squared is 1. This person is not different, so 0 squared is 0. Not different, 0 squared is 0. 1 more, 1 squared is 1. Added up, I get 2. I see the same thing for my green group, right? 1 above, square it, 1, exactly the same, so I get zeros. 1 below, I get a value of 1, add those up, I get a value of 2. I add my 4 plus my 2 plus my 2, and I get a value of 8. I can use that to fill in. So my total then is going to be 8 plus 8, or 16. I can do the overall evaluation where I subtract each person from the overall mean of 3. And if I go through and square them and add them all up, you'll see that you get 16, but we're not going to worry about that. Now we fill in our groups of freedom, right? My K is my number of groups. My N is my total number of subjects. So total degrees of freedom is number of subjects minus 1, gives me 11. Between groups, degrees of freedom, is number of groups minus 1, which gives me 3 groups minus 1 equals 2. And then I have my within group degrees of freedom, which is my total number of people, which is 12, minus the number of groups I have, which gives me a value of 9. If I divide across to get my variances, 8 divided by 2 equals 4. 8 divided by 9 equals 0.899999, or well, it's 0.88888. And then if I divide this by this, I get my F value. And again, F is just the ratio of the variance between groups to the ratio of the variance within groups. If we look at how this compares to what we get if we looked at SPSS, it's exactly the same. And any stats package that runs in ANOVA will give it to you in this format. Same kind of summary table, as it's called. Now, what I'd like you to be able to do is fill in these summary tables below, given, right, the information that's provided. And so you have to figure out how things are related, and you have to feel pretty comfortable with this. So in other words, I know that 2 divided by something gives me 2.5. And if I were to divide, if I want to figure out what that is, I can divide 2.5 by 2, and I get 0.8. Now, knowing that I have 0.8 in this 10, I know that this within divided, whatever this value is, divided by 10, is going to give me 0.8. So I ask myself, what is that value? I can figure it out by multiplying back. So 8 or 0.8 times 10 gives me 8. Likewise, I can figure out this one now, right? I know that 4 divided by something gives me 2. To figure that out, I can go 4 divided by this 2 gives me this 2. If I want to fill in these last two, I just have to add these up. 4 plus 8 is 12, and 2 plus 10 is also 12. Funny how those added up to be the same thing. Doesn't typically happen. Second example, right? I have some information here that I can start figuring out. Oops, gave you a little peek there. To figure out the between, I know that between plus within gives me my total. If I want to figure it out, I can just reverse operate it. 32 minus 16 gives me 16. I also know that 16 divided by my degrees of freedom will give me 2. Well, I know that that number needs to be 8. If it'll let me, well, it's not filled in. I also know that degrees of freedom between and within add up to 12, so I ask myself what plus 8 equals 12, and I find out that it is 4. Now I can divide 16 divided by 4 to get my mean square between, and then 4 divided by 2 gives me my F value. So one of the things you will have to do, and this is on the ANOVA quiz on D2L, take it. Got to be done by next week, otherwise it's a 0. Just throwing it out there. I'll send an email out to that effect. Just got to motivate you somehow. I'll let you work on this one by yourself and see how you do. But that's ultimately it for the ins and outs of how it works. Now, if we're going to use SPSS, and we're not going to, these are the directions if you ever need to, menus that you go through. Ultimately, you're going to get this output. And we can request descriptive statistics that give us if I'm comparing males and females and I just have 2 groups, it'll give me the means for each group, how many people are in each group, standard deviations, standard errors, minimum, maximum values. So that's great. The thing that I'm more interested in, though, is my ANOVA table summary. And this little slide is a good one to spend some time thinking about because it explains what everything is. Right? My between group sum of squares again represents how the extent to which why people are different can be explained by what group they're in. The within group sum of squares is all that difference that cannot be explained that exists within the groups. And the total represents the total amount of differences that exist in any population that I'm thinking of. My degrees of freedom are calculated here again. First one is k minus 1. Second one is n minus k. Third one is big N minus 1. My mean squares are my variances. This is the variance, the amount of variance that can be accounted for by group membership. This is the amount of variance that can't be. And the F is the ratio. The new thing that's added on is the p-value. We interpret this the exact same way. If it's bigger than 0.05, we fail to reject the null and say that there is no difference. If it is lower than 0.05, we say that the null is not right. We reject the null and we say that there is a difference. So when we think about the assumptions for this test, we have the same three we've been working on before: normality, homogeneity of variances, and independence. If you want to do these in SPSS, here are menus how to do it. But basically we know what those are. Normality, we look at the skewness and kurtosis, making sure they're between 1 and -1. If I want to look at it here, right, I have my aggression values. I see that, oh, my skewness here is all 0. My kurtosis, though, is out of whack. Really big low value, negative value here, and I have problems here and here as well. So that's not the greatest. I might not, be able to use ANOVA for that. If I'm looking at the homogeneity of variance assumption, there's an option in SPSS that runs the same test that was used in the independent samples t-test. It does it as an f-test though, and basically I'm looking at my Levene's test to see if this is bigger or less than 0.05. If it is bigger than 0.05, then I'm okay, and like in this case, I can run the ANOVA as usual. If it's smaller than 0.05, I have to use what's called the Brown or the Welch, Welch of the Brown and Forsyth tests. And each one of these are an option that you can use. I'm not going to go into how they're calculated or which one to use in which circumstances. Basically, pick the one that gives you the better result, and meaning that gets you the smaller sig value. On the exam and on some practice worksheets that I have, and let me see if I can pull one of those up quick. What I have are, and each one of these worksheet pages goes with a quiz. I have descriptive statistics for you to look at any issues of normality. I have the Levene test telling you whether or not you should use this or you should use the Welch or the Brown-Forsyth. In this case, and I'm just going to use this as an example, right, I'm looking at dosage of medication, 10, 50, 100, or 200 milligrams. And I took some readings and I compared how blood pressure had changed over time. This is real data, actually, so it's kind of fun to look at real data always. I have all my average scores. I have 10 people in each group. And that's all fine and good. If I look at, though, my skewness and kurtosis of groups, skewness is fine. But again, I have some kind of flat groups where I don't have a nice normal curve or a nice mound in the middle. It's a little bit flat, too many people at the end. So I have to be careful about what I did. When I look at this test of whether or not the variances are okay, because this is smaller than 0.05, I go down to the Welch and Brown and Forsyth. And if I pick the Welch in this case, I will reject the null. If I pick the Brown and Forsyth, I wouldn't. And again, each one of these is more powerful or better to use in some circumstances, but the biggest thing is that they get a little too strict, so my recommendation is just go with the one that gives you the smaller p-value. Note that if I would have went with my regular ANOVA, I would not have rejected the null. If I use the Welch, I do reject the null and say that there is a difference in dosages. And if you look at the mean stats, right, there are pretty big differences ranging from a decrease of 1.5 points to a decrease of 15 points, which is almost a 10 times each other difference. That's big, that's huge. It's just the within group variation was too much and the sample size is a little small to do anything. And so there are quizzes on D2L. I would recommend taking those a couple times. They're called the ANOVA quizzes with worksheets 1, 2, and 3. Take those for next time. The last assumption is independence of observations. Again, this is the idea that nobody should be affecting somebody else's score through cheating, through extortion, through bullying, or if somebody freaks out in the classroom and everyone else freaks out because of that, I shouldn't count those scores. That's a violation of validity and basic test protocol. So, the next thing then is interpreting whether or not, if I have a difference, my subgroups are different from each other. So if I go back to my eye color and aggression situation, right? I run this ANOVA. I get this ANOVA value, F equals 4.5. I have a p-value of 0.044. Because that is less than 0.05, I am going to reject the null. And I'm going to say at least one of the groups is different. Again, though, I have 3 groups in there, and I don't know if they're all different from each other or if there's just one group that's different from one other group, and that's it. Now, in SPSS, in order to figure this out, I have a lot of options. And this is the menu of how you would do it. And you would get some kind of follow-up test. And what follow-up tests are really a series of t-tests. And the t-tests come in a lot of different varieties, but they're all independent samples t-tests. And this compares the blue to the brown, the blue to the green, brown to the blue, brown to the green, green to the blue, green to the brown, right? And so some of this is redundant because I have blue and green compared here. I have blue and green compared here. The only thing that's different is the negative and positive sign. What I'm looking at here is for my comparisons of blue versus brown, blue versus green, and brown versus blue, do I have a p-value for any one of those groups that's less than 0.05? If I look at the green versus the blue group, there is my statistically significant difference. And what this says is that the aggression of the green-eyed people is different from the blue. However, blue is not different from brown, and brown is not different from green. Okay? Based on this 1.68 and this 1.68. Yeah, so and if you want to figure out what the t value is, like I have here, you just divide your mean difference by your standard area. That gives you your t score, and the t value here would be 3.00. Another example, I can look at this and start asking, well, what's going on here? How many groups do I have? How many examples? Or not how many examples. Are there differences, and if so, who is different? And so in this case, I have some score of social ability, and I am comparing it between different school sizes, right? If I ask you how many groups there are, the way that you figure that out is you look at the degrees of freedom, right? Degrees of freedom, here or here. Degrees of freedom between groups is always the number of groups I have minus 1. And so 4 minus 1 is going to give me 3. I always have to add 1 to my degrees of freedom between groups to figure out how many groups I have if I don't have the actual data. If I asked how many people total were in this, well, then I would look at my total degrees of freedom and add 1 person. And so I would get a value of 80. Now the next question is, are my values or variances homogeneous, right? And in this case, I look at my Levine stat, and I see that this p-value, again, the Levine test is testing whether or not my variances are the same. Because this is bigger than 0.05, that indicates that they are the same. And so I can use the regular ANOVA summary table. I don't have to go to the Welch or the Brown-Forsyth. I ask the question, are there differences? Well, because this p-value is less than 0.05, I am going to reject the null that says everyone's the same and say that no, there is a difference in social ability based on your school size. If I run the follow-up tests, I'm looking in here for any p-value that is less than 0.05. And I have one here, I have one here, and I have one here. And I also have one here. I'm going to have to get a drink of water in a minute. But the idea is that if I look at this, small schools are different from medium-large. Medium-small schools are different from medium-large, and they're also different from large. And my medium-large schools are different from my large schools. And if we were in class right now, we would graph this out, and we would see that social ability starts low in the small schools and gets bigger and bigger to the medium-large schools, and then it just kind of drops off. Meaning that once the school gets so big, it's really easy to find other people like you, and you just kind of hang out with, if you're a jock or a geek or a nerd, or an alternative person or a gothic person or an artsy person or whatever, right? You just hang out with the people who are like you, and you don't really have to deal with anyone else, and it becomes really easy to see other people as just strangers or other people that you think are ridiculous, right? In small schools, you're not exposed to that much diversity. But when you get around 100 people, it's not like you can avoid people, you know? So you're confronted constantly with people who are different from you, but you learn to get along with them. And so that's basically what all this would be saying. What you need to be able to do is look at this stuff and answer those questions. How many groups? Are there differences? Are the variances the same? If there are differences or if the variances are the same, which results am I looking at? The regular ANOVA or the Welch and the Brown Forsyth? When I look up figuring out who is different, then I look at these tests and just look at all my different little p-values. And I'm looking for anything that is lower than 0.05. Again, all of this information is kind of on there twice, so be careful that you don't repeat yourself. Now, when I do this, I am running a whole bunch of tests, right? I'm making one comparison here, one comparison here, one comparison here, another comparison here, and a final comparison here. So I'm making 6 different comparisons. Now, when we talk in the past about type 1 error rates, it's the odds of saying there's a difference when there's not. And so when we think of type 1 error rates, these are our false positives, right? I say that a treatment works when it doesn't. I say that my brain grain pill works, but it don't, right? I say that there's a wolf and there's not. I say that somebody committed a crime and they actually didn't. Now, when I'm looking at this, if I set my alpha level at 0.05 for each test, it means that I have a 5% chance of getting a false positive each time I run that test. So if I keep going, I'm really pressing my luck. So suppose that you're on Wheel of Fortune. It's the same kind of thing. And say that there are 20 different things on the wheel, and say that I have, out of all my 25 things, I have, one bankrupt or a bad card. And so if I look at overall, what's the probability of, out of 20 things, I should say, I have 1 chance out of 20 of getting a really bad outcome that I don't want. And so on the first spin, I have a 5% chance. On the second spin, I have a 5% chance. Third spin, because all these probabilities are independent of one another, right? Just like flipping the coin over and over, right? 5%, 5%, 5%, 5%, 5%. And it stays the same for each one. But when I consider them as a group, I am probably going to, if I keep spinning, I'm going to get a bad outcome eventually. And so, the question is, right, say that you're on the show and you have $10,000. And Pat says, hey, I'll give you 50 grand if you spin the wheel 25 times without getting a bankrupt or lose a turn. Would you take this? If you get one of those, you wouldn't. Now, most people say that I wouldn't do it because the odds of me getting a bankrupt on one of those 25 spins, right, is pretty good. And I know that intuitively that it's going to happen eventually. So I would really be pressing my luck, and I think I'll take the $10,000 and run. Suppose he offered you the deal, though, and said you just have to spin it once, right? And you only have a 5% chance of losing $10,000, but you have a 95% chance of gaining $50,000. Most people would do it. And if he said, well, maybe you got to spin it twice. Maybe you have to spin it 3 times. And some people would keep doing it, keep saying yes and yes and yes. But at some point, usually around 8 is when the last people fall out, who are really, risk tolerant. They say that if he asked me 8 times or more, I wouldn't take the deal because the odds of me getting one of those bankrupts just gets too high. In the case of 25 spins, we can actually calculate the probability, and the probability of getting at least one bankruptcy is 72, or 0.72 or 72%. And when we're making comparisons, we can think of it the same way. And so say that I have just 2 groups, or I'm running 2 different tests, right? And suppose that in this case, right, I set my alpha level at 0.05, so there's a 5% chance for the first test that I will reject the null, 5% chance for the second test. In both cases, there's a 95% chance that I won't reject the null. If I break this down and I figure out probabilities by multiplying them across, there's a 5% chance, right, that I'll reject it for test 1. There's also a 5% chance that I'll reject it on test 2. Now, the odds of both of these things happening is really, really small, 0.2% or 0.25%. However, the probability of me rejecting the first one and not rejecting the second one is about 5%, 4.75. For not rejecting the first but rejecting the second is also close to 5. And not rejecting either is pretty good, about 90%. So when I add up all of these different probabilities for having at least one rejection, kind of like we did with the flipping the quarter, right? Probability of getting at least one head. Probability of me getting at least one rejection is almost 10%. And so among these 2 tests, my error rate, or the rate at which I would get at least one false positive, is now almost 10%. And we can do this for 3 tests and 4 tests and 5 tests. And there's a short way to do it, but the idea is, right, in each case, I'm basically making my little decision tree. With 3 different tests, like flipping that coin 3 times and coming up with those sequences that I could get. To reject them all is really unlikely. To fail to reject them all is actually pretty likely because there's such a high probability of not rejecting. But all in all, if I look at what's the probability of me getting at least one rejection when the null is actually true, it's almost 15%, or almost 3 times what I started with. And if we look at it, right, the simple way to do it is that I just multiply however many tests I have by my type 1 error rate, or my alpha level. And then in those cases, if I got to 20, I would be guaranteed basically to have one test that was a false positive. The more accurate, or the real way to do it, is this equation. I'm not going to go into it that much, but the idea is that the more tests I run, the more likely it is that I'm going to have a false positive. And if I keep doing it, things are going to come out eventually. When we look at research that's published, there's a huge bias against false positives because they only publish things that find relationships or find differences. And all the studies that people do that don't find differences don't get published. So recognize this and realize that I have to do something about it. Now, the short answer is that I do a correction. And basically, I reduce my comparison alpha level for each comparison, and then it kind of balances out overall. And there's a ton of different options. All of these represent different ways that I can do it. They're all good under different circumstances. I'm not going to go into a ton of time, but the most commonly used ones are the Fisher's LSD, not a drug, just what's called a post hoc test, and then the Bonferroni. And the Bonferroni is by far the most common. It's the simplest to understand. Basically what I do is if I have 2 comparisons, I divide this 0.05 by 2. And so I have a different p-value that I need to compare it against. What SPSS does for you, though, is it makes those adjustments and gives you an adjusted p-value. So again, I'm really just looking for anything that's less than 0.05. In this, I did the Chaffee test, which can get pretty strict, the LSD, which you only use when you have 3 groups, the Bonferroni, and then the Citic. And if you look at them all, they get slightly different results, right? But all in all, they're pretty close to the same. In particular, if we look at the Chaffee and the Citic, and even the Bonferroni, they're all really close. The LSD gives me smaller p-values in general, and it's a much more powerful one. You don't need to know which test to choose, but you do need to know how to read this. And so if I'm reading this, I'm looking through, right? And I'm just going to give you one test. And I see a number less than 0.05, so blue is different from green, and that's it. And that's I'm done. I'm done with my analysis. So basically, what we're doing is doing a bunch of t-tests between all my different groups. If I have blue, green, and brown-eyed people, I want to compare blue to green, blue to brown, and green to blue. And then I'm done. What you need to know is what's going on, what family-wise error is, and how we control for it, basically by doing these different Bonferroni, Citic, and modifying our alpha level, and then how to interpret the output and the research. And there'll be another video about looking at research. You have an assignment to that will be due this next week. And this is the end of video 1. Hopefully, it'll help you navigate through those quizzes on D2L. There's one for ANOVA. There are 3 other ones for reading output. And look at the practice test and see if you have any questions. All right.